Okay, so back to hyperbolicity. And the last two lectures were really just giving a context, the motivation, the specific class of examples. Today I'm going to introduce the main technical geometric construction that is really fundamental in the work that we do. It is actually very elementary, but has some fairly deep consequences. And so I'm going to introduce the notion of what I call hyperbolic coordinates. So this concept is inspired by some of the techniques in the Benedict-Carlson work that I mentioned yesterday, which really set out the fundamental point of view. Okay? But in that paper, these ideas are kind of very hidden and not systematically developed. So I would see this as a kind of mature version of what is in those papers. So we'll start in a very general setting, and then we will apply it in a very specific setting. So for the moment, let's just assume we have some map phi from R2 to R2. And let's suppose that we have some psi 0, some point in R2, and some k greater than or equal to 1, okay, such that the determinant phi I psi 0 less than 1, which is less than the norm of d phi by k. So what does this mean? This simply means the fact that this norm, so if we look at the point here, we have 0, have the map phi k, maps to point psi k, and then we have the derivative that acts on the tangent spaces. So this is tangent space is 0. This is the derivative d phi k. This is the tangent space phi k. And as you know, linear maps, we take the unit circle here. As you know, linear maps map circles to ellipses, okay, or which might be circles themselves. So this condition is basically simply saying that this linear map maps a circle to an ellipse with two different axes, right? So this says that this derivative is bigger than 1, that the norm is bigger than 1, so there must be at least one vector that is bigger than 1, but the determinant is less than 1, so the area is not expanded. So all this means is that we have an ellipse. That we don't have another circle, so the map is not complete. This is an extremely simple and elementary observation, but it has some really remarkable consequences. And we will point out the following. So here we have the axis. If you have an ellipse, you have the major axis and the minor axis. And we have, these are orthogonal, obviously. We have also the pre-images of these two axes. Now, even though this is such an elementary fact, I think it's certainly, when I started studying this, I did not know that the pre-images of these are also orthogonal. It's a fairly simple geometric argument. You can just basically think of the inverse, and then you will see that if you take the unit circle here, these two directions are mapped to the to the major and minor axes of the ellipse here, which are exactly these directions. So you get something like this. You get that here you have what, let's call this EK. And here you have an orthogonal direction I will call FK. Okay? And these are the pre-images of the major minor axis, and they're themselves orthogonal. So we have an interesting kind of orthogonal basis that we can use for this derivative, right? We do not have any information on, at this moment, at this stage, we have no information on where these two vectors are or where these two vectors are, but let us call, we call, let's use some kind of notation, and let HK is this set of vectors, EK, FK. Here we will call hyperbolic coordinates. And notice that if you write this derivative, so first of all, let me point out, let me also introduce some notation here. So let me write this vector here as F AK, and this vector here is E AK. It can be useful to write it like this. And notice that, of course, FKK, just the size of this is just the norm of the matrix. Is equal to the norm A by 0. And in fact, again, if you just think about it a little bit, this is just the norm of the inverse, this matrix -1. This is the conorm. This is the most contracted vector. So in terms of our hyperbolic point of view, the importance of these two vectors are that this is the most contracted, most expanded direction here, and this is the most contracting direction. So it is a kind of, we're not looking at any hyperbolic invariant splitting, but we've identified expanding and contracting directions. So you can you can use these as coordinates for these tangent spaces, and in these coordinates, so in hyperbolic coordinates, so I'm using a little bit of abuse of notation here. So here I'm thinking of these hyperbolic coordinates in the domain and their images in the range. But in these hyperbolic coordinates, we can actually write this derivative in a very simple way. D phi k is just simply a diagonal matrix that is just here in FKK is going to be the norm of FKK. Okay, which is in fact just so this will turn out to help us a lot. We're saying that we have a very simple diagonal form for the derivative if we use these particular coordinates. So how does this help us? Well, it is easy to see that these coordinates depend continuously, in fact depend differentiably on the initial condition. If the map, they depend only on the partial derivatives of the map phi, so they have the same regularity as the partial derivatives, you can see that. So if phi, for example, is C2, then for nearby points, you will still get a circle mapping to an ellipse, right? So if these hyperbolic coordinates are defined at a point psi 0, they're defined in a whole neighborhood of a point psi. Okay? And they depend, if phi C2, they depend C1. So they give rise to two unit vector fields in the neighborhood of psi 0. Right? So let's define it like this. So let's define this notion of hyperbolic branches. So if we have these defined in some whole region like this, so let's suppose we have some region UK, and let's suppose that this conditions is satisfied at every point of UK, the neighborhood of some point size 0, then you have at each point, you have these directions. You have EK, you have a vector field here, and then similarly you have a vector field. You have the orthogonal vector field here. Okay? And because these vector fields are C1, then they are integrable, uniquely integrable, and you have two foliations, right? So you have a foliation which is tangent this direction. Another orthogonal foliation okay? So we have EK equals foliation most contracted integral foliation most contracted direction. Directions. Okay, and similar for FK. So this is a very interesting foliation because it is really the integral curves of most contracted directions. So when you iterate this map, they contract, right? Because they are defined precisely by the fact that their tangent directions are contracted. So when you apply the map by K, you will get some contraction in that direction and you will get some expansion in this direction. We don't have any quantitative estimates yet, but morally we have this kind of picture. So we have more or less something. I'm going to purposefully not put it, oops, we don't know that it comes in any nice way. It might bend like this, we don't know. Okay, but we have the image of these foliations is also, because of what we just said, is also two families of orthogonal foliations, which does not mean that this thing cannot bend, right? This is a little bit counterintuitive, but obviously you can have orthogonal foliations where this has, let me even emphasize this by having some kind of curve like this, so you can have like this. Okay, so these foliations we will denote by EKK and FKK. Okay, the images. Okay, so this is a geometric structure that just exists. Notice we have done nothing. Right? I've assumed almost nothing, but it exists. And it is a kind of, I often call it finite time stable and unstable foliations, because they only use information about the finite time. So of course, one of the key properties of the usual stable manifolds and unstable manifolds is that they are defined to have an infinite time property, right? The stable manifold is all the points which eventually asymptotically converge to each other. And so for the unstable manifolds in backward time, this has a very big importance. Similarly, the usual splitting in the hyperbolic systems is an infinite, so you have an invariant splitting forever, okay? But in some sense, these have their own real significance. So these are, at a finite time, the analog of the natural analog of the stable foliations. In some sense, even more natural than the real stable manifolds. Like this point here might have a real stable manifold somewhere here, but this is really the curve of the most contracting directions at time k. Right? In some sense, if you look at time k, then this is the curve that it's just a heuristic remark that it has some relevance. Okay, a lot of this work has to do with, and a lot of what Benedict Scarlson did that was remarkable is set up structures for finite time dynamics. Right, this is the whole point, because we are trying to construct hyperbolicity in these families. So we're going to be having to exclude parameters that fail certain conditions, but up to time k, we can only use information about the dynamics at time k. So we're trying to construct alternative hyperbolic structures that are related to finite time dynamics. This is the first one. Okay, so we're going to be interested in when these, we're going to have to put a bit more conditions, of course, because we're going to want to prove something about this. So far, there's really very minimal hyperbolistic conditions. Let me give first a definition, because we will be interested in when some of these curves are horizontal, right? So I will define the notion of an admissible curve. Definition, we say a curve, C2 curve, gamma is admissible, basically if it's all its tangent directions are almost horizontal and its curvature is also small. So if tangent directions, tangent vectors have slope less than equals some kappa, some, if I draw, when you use LaTeX, you can distinguish between kappa and k, but on the blackboard, I don't know how to do it, so let me use eta less than 1/2, and curvature also less than equal to eta less than 1/2. Okay, so this is just, we will be using this a lot because we will try to control the slope and curvature of certain curves. And then let me say that we say that UK, so we call these quasi-hyperbolic branches. So at the moment, we'll call these just quasi-hyperbolic branches because there's no real assumptions. We will need to put a little bit more assumptions. This is a quasi-hyperbolic branch so far. It has this geometric structure. So a quasi-hyperbolic branch, phi k UK, a quasi-hyperbolic branch consists of this domain UK, and this map phi k is admissible. If the leaves of the foliation fk are admissible. So if this foliation is admissible, let's say, by which I mean the leaves are admissible, so a little bit like this picture, and is fully admissible if also the images are admissible. This is also. Okay, so as I said, there's nothing to say that these, we just have two orthogonal foliations. We have no idea about whether they curve or anything. So we just define this notion of admissibility and full admissibility. If, of course, notice that if the unstable leaves are almost horizontal, then the stable ones are almost vertical, right? So any statement about the admissible foliation, about this unstable foliation is also a similar statement about this other one. So now I'm going to give the definition of a quasi-hyperbolic branch. I'm going to give it all. I could just say that it's roughly a little bit of a quantitative version of this, but just to show that that it's really not very many assumptions that we give. fkk, the image. So we look at this branch because the fact that these are admissible doesn't mean that this image cannot be doing all kinds of things. So we want also the image to have horizontal leaves. So it's basically just going horizontal to horizontal. You know, this is just shrinking hyperbolic and it stays horizontal. So let me say what we need to actually prove some interesting things about this. So let's say, given gamma b greater than 0, we say that this phi k uk is a hyperbolic branch. So we give a little bit more quantitative. So for all points psi 0 in UK, and for all I immediate steps, like psi I equal to phi I psi 0, we have the following three conditions. So one is just a more quantitative version of this. So we have that 0, the determinant of d phi psi I should be less than b, should be less than gamma to the minus 400. This, of course, will not, this quantitative will not be used in these lectures, but that's what we've got in the paper. Less than 1/2, less than 1, less than the derivative. So this is really just putting some numbers on this, right? This is, again, saying that the determinant is less than 1, the derivative, the norm. So this is at each step, but of course this means in particular that the product, the determinant of the product is also less than 1 of the composition. And it's just putting some numbers here which will be important. In your mind, you should think of gamma as the maximum derivative in your system, more or less. Along certain orbits, it's like a large number, and b is a small number. So b corresponds to the, morally, to the dissipativity in the Henon map. Right? So we're thinking of b as relatively small. Then it will come out in the calculations how small it needs to be. And then we need some conditions on the map. So we have that the some bounds. So we have that phi I C0 should be bounded, the first and second derivatives. So in C2, this should be bounded by gamma 2 to the I. So this is just saying that the first and second derivatives do not grow exponentially more than at the speed gamma 2 as you iterate. And also we have that the phi at each particular point and the second derivative, like psi I, also is that. So I'm writing these, I will not do any calculations that use this here, right? But I'm writing it because I want to show. So if, for example, in the Henon map, if you have a diffeomorphism where the derivative is bounded in your whole region, these are automatically satisfied. In our case, remember, I emphasized that we have a point of discontinuity with unbounded derivative. So these conditions will mean that we need to, the orbits we look at are not allowed to come too quickly, too close to the singularity, right? So it's saying that we need to look at the branches that have some kind of bound towards the singularity. But these are just automatically satisfied, for example, in the Henon map. And then we have some conditions that say that vertically you contract. Okay, these are also very mild conditions. So these are conditions on the partial derivatives of the map. So this is bounded below, and then we have all the other partial derivatives, dy by 1, dy by 2, the x y by 2, phi 1, phi 2, okay, basically all the other partial derivatives should be with y. All the partial derivatives that have y should be small. Okay, for phi I. Is this sorry? There's no I here, yes. So again, this is really just saying that the dependence on y is very small, so it's just to do with the dissipativity. Okay? So again, I won't be doing any calculations, but I want to put them because paradoxically, I want to emphasize that they're very mild conditions. Okay? They're very mild and general conditions, especially because the consequence of this are going to be we're going to prove quite a few things about this geometric structure that are not at all obvious and that use these properties here. So what do we prove? So the first remarkable thing, what are the kind of things that we're interested in proving? There's two fundamental things we're interested. First of all, how does this structure change with k? Right? So when you iterate once, suppose you have all this structure time k, and now you iterate, you take phi k plus 1. Okay? Does this structure continue to hold if it holds at time k? If it holds, what is the relation between these foliations at time k and the foliations at time k plus 1? Because obviously this is what we're going to be doing. We're going to be iterating these regions. And because this structure depends very much on k, right, we need to understand how it evolves with k. So the first proposition is that, in fact, these structures converge with k under these conditions. These are conditions that say that you have some hyperbolicity. And so the first proposition is that, using the fact that B is kind of small, we have, first of all, that if we look at the first, so the contracting direction at time 1, so you suppose that I equals 1, okay, you have these integral curves just for the most contracted direction and the 1 iterates. This is actually the stable is very close to the vertical direction. So this is less than or equal to gamma squared B, in this case. So you think of B as small. So at time 1, when we look at the structure time 1, we have basically an admissible, okay, we have basically an admissible branch because we have almost vertically, well, this statement for the moment is not for the curvature, but morally it's kind of almost vertical. And we also have that so where is it? So E I plus 1, as you go from one to the other, this is also less than or equal to gamma e to the I. So as you iterate further, this gives a Cauchy sequence of directions, actually. So this means that when you look at this structure at time 1, you get a certain structure. You look at time 2, and then these all these vectors, the corresponding vectors, have a certain distance from those. But as you go further and further, this distance becomes smaller and smaller. So this whole structure is converging to something. Okay? As long as you can keep this going, as long as you can keep those properties going, of course. In general, you will be able to do that by shrinking this region, okay? But in principle, all this thing is converging. You get a Cauchy sequence. In fact, you can use this as a kind of, in some cases, as a approach to the stable manifold theorem, where this converges eventually to the real stable manifold. We also have that these directions are contracting. So if you look at the image EKK, and this is contracting, or EKI even, it doesn't matter. You can even take the most contracted at time K, and you can iterate it for I, and it's contracting. One important observation that I didn't make is that this orthogonality of the image only works for the K directions at time K, right? if you can think about it a little bit, but if you define these directions at time k, and you look at the images after 1 iterate, 2 iterate, 3 iterates, intermediate iterates, they are not orthogonal, right? So this orthogonality really is related to the fact that they have been defined and they map to the major and minor axis at time k, but if you look at the images of this at intermediate steps, they're not orthogonal. So miraculously, they return to an orthogonal situation there. Okay, so this is a very interesting and very important property of this. And the second crucial property is that has to do with how it changes on the regularity, right? So you look at a direction here. So you look nearby contracting directions. What's the regularity of this? As we said, they change C1, they depend C1, but we can show that in fact the derivative of these directions with respect to the phase space, so we can write it like this, derivative of this direction in terms of how it changes is also bounded. Okay, in this case we get gamma 75. These numbers are not so important, but the crucial point is that we have a B here. B is small. So what this is saying is that these hyperbolic coordinates vary slowly with the phase point. Okay, the philosophy is B, so there's a small variation. This is really a calculation. So there's not very many sophisticated arguments, but it's a remarkable fact. Adim likes to say that it is the heart. More or less everything, the whole argument and the whole paper depends very much on this fact. I am not going to go into this, but we have a crucial point in the actual paper is to talk about also the variation of these things with respect to the parameter, right? It gets really quite technical when you talk about that, but you also want to know, because we are talking about parameterized families and we're changing the parameter, and we are therefore important to understand also how these structures change with the parameters. And the real heart of the paper is a similar proposition that says that you get also slow variation with respect to the parameters. So this whole structure depends very slowly with respect to the parameters. It's about 5 pages of calculation here, but it really is just taking the formula for these and differentiating it. Okay? It's just a complicated differentiation, and we get this. And a lot of what I'm going to say depends on this fact. So as an immediate corollary, we get admissibility of these branches, right? Because this property here says that the stable directions are almost vertical, which means that the unstable ones are almost horizontal, right? And this one basically says that the curvature is small, right? So because this one says they vary slowly. So as a corollary, we just get that every hyperbolic branch is admissible. Not fully admissible, and we will get to that now because we don't know what happens to the image, right? These two are kind of independent, and it depends what happens. And that is the remarkable thing, is that this corollary, these statements, do not know the geometry of the images of these branches, right? They only know, in a very minimal sense, the hyperbolicity of this. So the slow variation here just depends on the fact that we have these hyperbolicity estimates, but nothing about the geometry of the images. Okay? We're interested, however, and that's what I'm going to talk about, we're interested in trying to get these hyperbolic branches to be fully admissible, so we want to control the geometry of the images, and this is what I'm going to talk about now in the remaining 5 minutes. So for this, we want to go a little bit back to our setting. Is the Lorentz map, although we will not use the properties in a very fundamental way. I remind you remind you what the picture is. If you remember, our setting was that we had this return map. So we have this discontinuity line. We have this cusp here. This fold here. This is a tiny, tiny fold, but I'm drawing it big for convenience. Cusp. And we have these critical regions. So this here, call it delta C. This is the region that gets mapped to the fold. Right? So this whole part of the rectangle gets mapped to this cusp, and this gets mapped in an obvious way. So you take this whole half, it gets shrinks because it's highly dissipative. It gets stretched, as you know, because you have this hyperbolicity, and then it gets mapped by the flow back here, but then this last bit gets folded, so this bit here comes to this side, and this comes to this side, right? And the rest is what's mapped to here. This is the geometry of this picture, right? Similarly, we have delta minus C here. Minus C. And then we also need to control a little bit what happens. As I said, we need to worry about the unbounded derivative near the discontinuity, because we do use, especially for the, for both of these estimates, we do use very much the fact that we cannot, there's some kind of bound of the growth, and so we do at some point also need to worry about the discontinuity. So this is a neighborhood that we have to control. That's why, that's one of the main differences between the Henon map, is that you need to be careful about what happens here. This delta 0. And so one of the facts that comes from the definition is that this map, the map phi, so let's say that this map now is our map here on the square. So phi is uniformly hyperbolic outside delta 0. Is uniformly hyperbolic. Sorry, outside delta C. Outside delta plus or minus C. And you can kind of believe that, right? This very strong dissipativity, and we do have very strong contraction, very strong stretching, just like in the geometric model. It's just here is where things go wrong, but here everything, all the expanding directions, the horizontal stay horizontal, the vertical more or less map to vertical, and here also, except everything is turned around, right? So here, the horizontal direction gets also mapped to a horizontal direction, but with a twist. So as long as you stay outside delta C, everything is nicely uniformly hyperbolic. Okay, and we will. So if we have a hyperbolic branch, suppose we have a hyperbolic branch and its images stay outside delta C. So if we have a hyperbolic branch like this one here, and we suppose that the image does not intersect delta C and also does not intersect the singularity. Okay, so if we, outside the singularity, we have uniformly bounded derivative. So we have this, we are guaranteed that we have those condition 2, for example, on the bound on the derivative. So this is sometimes called, if this is empty for all intermediate iterates, okay, then we call this phi, this branch, phi k uk, we call a non-critical hyperbolic branch. And then actually it's not difficult to see for anyone who has some experience of uniformly hyperbolic systems that if you take an admissible curve, so if you take a curve that is in the unstable direction with small curvature and you map it inside a uniformly hyperbolic region, then it remains admissible, right? So because that's what uniform hyperbolicity does, because here it's not just uniformly hyperbolic, but the contracting directions are all almost horizontal here, and the contracting almost vertical. So that means that if you start with a with a hyperbolic branch, which therefore is admissible, and you take these unstable leaves, so if here you have some little hyperbolic branch, in fact, let's draw one here, because let's draw. Suppose we have hyperbolic branch. In general, these hyperbolic branches will stretch all the way from here to here, because after one iterate, they then get shrunk very much and they end up in here, right? So here we have some, it's natural to think of these initially as being large hyperbolic branches. So the fact that this lands on a fold, I've drawn it here on purpose because we will use that, but it doesn't see that, right? You only see this fold when you come from the critical region. If you just start here, all you see is a uniform hyperbolic map somewhere here, right? So here we have, if we assume that this is a hyperbolic branch, then we have these stable and unstable, and here this is admissible because of what I said. So these are almost horizontal, and this will map to somewhere here, right? It will map something like this. Okay. It immediately gets very small because, of course, it's inside the image of this. And because this is uniformly hyperbolic, then these curves, which we've just shown that are admissible, they're almost horizontal and they have small curvature, will map also to admissible curves with small curvature. And therefore, at least after one iterate, this will be a fully admissible hyperbolic branch, right? Because it will have the property that not only Fk are admissible from that, but the images are also admissible. And we can just continue that as long as we stay outside delta C, then we continue to have this uniform hyperbolicity. So we have this, again, this corollary of this uniform hyperbolicity, if that every non-critical hyperbolic branch is fully admissible. So we take a hyperbolic branch, as long as it stays outside, it will be fully admissible. So we have a very good control over the geometry of these finite time stable and unstable foliations. So, I think I will have to stop here, because what we want to do next is, let me just say a few more words. So this is the foundation. Okay, this is the main geometric object, these hyperbolic branches, the admissibility and non-admissibility of these hyperbolic branches, and the observation that we have divided our phase space of our system that we're studying into these regions outside delta C, where we have uniform hyperbolicity, outside delta C and delta 0. Everything works well. So this whole structure satisfies. I should have said also that these conditions are satisfied outside delta C and delta 0. So this property actually holds out everywhere outside delta C, but I've assumed that it's outside delta 0 to make sure that we satisfy this condition 2 of the hyperbolic branches. And what we're going to look at tomorrow is what happens now when this hyperbolic branch lands in delta C, right? So when it lands in delta C, then that is the way where we lose the hyperbolicity, right? And what we're going to show, and it's very difficult to keep track, that's the whole point, is that when you fold, then you lose the hyperbolicity completely. And the key is going to be to look at the image of this inside these hyperbolic coordinates themselves. The key strategy is now to be able to control this fold using these hyperbolic coordinates.